Hey everybody, I'm Gage Anderson, and this is a brief walkthrough of my complexity analysis application. The point of this application is to take an arbitrary Python function code, and given that code and some input arguments, spit out an estimate for the computational big O complexity of that code. Without further ado, we'll get into the walkthrough. So this is the web application hosted on AWS. This is the sign-in screen. It's done with AWS Amplify. So right here, we'll click on the account I already have, sign in. So when you sign in, you're given this page right here for the editor, and you're given a few options. So the first thing that you do on this page is you put in some input arguments. So right here for the input arguments, we're going to put in x. And we're given a few options for what argument type we want to put into our function. So we're given int, string, list of int, list of string. We'll stick with int for now. And then we're given this checkbox below that, vary this argument. So what we do when we select vary this argument, we're giving the backend the ability to change this argument to produce a runtime versus input size graph of the function. And that's what allows the computational complexity estimate to happen. So say, for example, your argument is n, and you want to vary n to produce a complexity estimate. So you'd get O of n squared, O of n cubed by varying how large the input size is for n and seeing what the shape of the graph is for runtime. This will make more sense when I show the results later. So for now, we'll put in x, which is an integer, and we'll set the maximum input size to 1,000. And you can see it's added to the argument list. Optionally, we can enter a code description. So I've entered that it's a doubly nested for loop. And you can see down in the code editor that we have a Python function body right here. The def function header is assumed right here. And it's a doubly nested for loop right here. And if you recall, doubly nested for loops with respect to the arguments are x squared or n squared. So right here, we're expecting a n squared result, O of n squared complexity for this code editor. So we have everything we need here. So now we're going to submit these asynchronously to the backend for analysis by hitting Analyze Code. So we've submitted the code and arguments to the backend now. So while we're waiting for that to analyze, we'll go to the Results tab. And as you can see, for the account that I'm logged into, there's been a bunch of previous analyses. And you can see what you're able to do is you're able to access your previous attempts at analyzing complexity versus runtime. As you can see, the output here is a runtime versus input size graph. There's a lot of different previous analyses here. Let's refresh the results to see if there is the latest result there. And there is. So we ran the code 1158. This is the most recent one. So we'll get the runtime graph. So here's the runtime versus input size graph for the doubly nested for loop that we just ran. You can see it's a rough O of n squared shape where the runtime is small at the start and it increases with the square of the input size. And as you can see, the complexity estimate is O of n squared for that. So the algorithm was able to get it right. So a few of the issues that I had to work through when making a complexity analysis tool that actually worked was actually choosing what polynomial I should put as my output for the complexity estimate. For example, this could also be an O of n cubed result, and we could fit an O of n cubed function here just with a small coefficient on the n cubed term. So what I did to rule out those larger terms if they were not significant is I made an arbitrary cutoff value for the coefficient on the polynomial terms. And if that cutoff value was too small, I cut that out of the answer. So say, for example, an n cubed function would fit this better than an n squared function. What I would do is I'd look at the coefficient starting with n cubed and say, do we really need this? Is it significant enough? And if it was too small, I'd cut it out. So that's how I was able to distinguish between what polynomial the functions are. And also, the backend analyzes the possibility that it's log n or n log n or several other complexity classes like exponential and factorial and compares all of those. And the way it chooses the answer is it finds the minimum squared error function among all of the different complexity classes analyzed. So this one gets O of n squared. Now, just a few caveats with this technology. It's impossible to know exactly what input size you're going to need in order to have a complexity output that makes sense a priori, because you don't know exactly when the function will time out or how long it will take. It takes some user experimentation in order to get a big O complexity graph that actually makes sense for this. So use some trial and error, use some discretion, use your input arguments wisely, and you'll eventually be able to get a graph that makes sense for whatever input function that you've done. One more thing that I had to work through was making sure that the input code into the function was secure. So the user can enter an arbitrary Python function here. However, on the back end, this is run in a secured environment, so they're not able to call OS-related operations, etc., so that no malicious code is able to mess up my backend environment. The backend environment for this is all run on an AWS serverless system using API Gateway, using Lambda, using DynamoDB, etc. So that was a brief walkthrough of my complexity analysis application. Feel free to reach out if you have any questions or concerns. Thank you very much.